Okay, so I think we can start again. Welcome, everyone. My name is Mariangela Pellegrini. I'm the Educational Patient Program Manager for the ERN-EuroBloodNet, so European Reference Network on Rare Hematological Disease, and I'm very honored to welcome all of you on the last session of this educational program organized by GenoMed4All at the ERN-EuroBloodNet and dedicated to artificial intelligence in hematology and conceived for public at large. As said, this program has been conceived, planned, designed by the scientific committee of the GenoMed4All, the educational committee. And it's, as you can see, it's an European on-live and interactive program. So you will have interaction with all of our speakers. And so our objective is to increase awareness in the growing role and growing advances of artificial intelligence in medicine, so meaning diagnosis, treatment, follow-up. And we have also tackled three specific clinical domains of hematology, that is myelodysplastic syndromes, sickle cell disease, and multiple myeloma. As said as I've just said, this program is a cycle of 4 webinars. Today we are at the last session. Each session has been provided by key expert speakers in the field of artificial intelligence and application of the artificial intelligence on rare hematological disease. We started on the 13th of September. On the first lecture, we have presented the GenoMed4All, the role of precision medicine in hematology. We have presented use case on MDS, sickle, and multiple myeloma. Last time we talked on data standardization and linkage, and today we are going to talk about data integration and analysis. But before introducing you the three speakers of today's lecture, I would like to share with you some key roles and home roles. So first of all, as you can see, this session is recorded. So if you don't feel comfortable with that, you can switch off your camera, change your name in the Zoom platform, or just write to me and I will take care for the recording that your name will not appear if you intervene in the Q&A session we will have at the end. And as said, at the end, so we will have first the speaker presenting the lecture and the topics, and then at the end you will have the possibility to raise your hand and ask orally the question, or to write the question in the chat. And as you can see, we facilitate the interaction with the speaker using Slido. That is extremely easy to use Q&A and polling platform for meeting and events. So you can see there is a barcode that is actually displayed in the screen. If with your mobile phone you click on it, you can go directly to the Q&A box and write your question. So we will tackle all your comment, question, feedback, curiosities at the end of the presentation. So said so, your microphone will be muted along all the presentation, but feel free at any moment to write your question in the chat. And if you want to intervene orally, that will be at the end, raising your hand. So we can finally arrive at today's lecture, so data integration and analysis. The three speakers I'm going to present are Tiziana Sanavia, that is assistant professor at the Department of Medical Science in the University of Torino in Italy since 2020, and she has a PhD degree in bioengineer from the University of Padova. Then we will have Patricia Alonso de Apellanis, that is assistant professor at University Politécnica de Madrid in Spain since 2022, and she's currently pursuing the PhD degree in deep learning algorithm for medical applications. And finally, we will listen from Gastone Castellani, He is full professor at the Bologna University in Applied Physics, Biophysics, and is also the director of the Galvani Center for Bioinformatics, Biophysics, and Biocomplexity. So please, Tiziana, you go first. The floor is yours. Thank you very much.
Thank you for the introduction, Mariangela, and welcome everybody. So I will share my presentation. Can you see it?
Yes, perfectly. Thank you.
Okay. So I will introduce you what we are doing in our research lab when we are talking about disease progression prediction. So let's first introduce the topic of today, which is the artificial intelligence. So I would like to first point out that the concept of artificial intelligence that is broadly mentioned and that one of machine learning are not the same concepts. They are quite different because artificial intelligence is a very general concept that includes all different techniques that tries to mimic the human behavior in order to solve some problems. In the 80s, the machine learning arose. So with the machine learning, we were able to provide some models that are able to learn from data some new rules. So what we mean when we say we learn? So in the conventional programming, we were used to provide to the computers the data and some rules that were human created. And we let the computer to find out a desired outcome. In the machine learning, we change our paradigm and we provide the data and what we expect as a desired outcome, and we allow the machine to create their own rule through a learning process. So it automatically assesses the rules that creates. In order to address this task, we have to prepare the data, and in our case, the clinical data, in a suitable way that can be exploited by the machine learning algorithms. So here you can see an example, and we have the information from each patient, and we distinguish two categories of variables, of clinical variables. On one side, we have the features that are used from the model to build the rule. On the other side, we have what we call the outcome. So, for example, a specific clinical event that describes the prognosis of the patient. And each outcome has a label. For example, the outcome, the event happened or not. With machine learning, starting from this data, we can perform a plethora of algorithms that can address different tasks for the clinicians. A first approach is called unsupervised approach, where we observe and learn new patterns from the data, and we allow to group the patients according to similar characteristics that we found in the clinical records. Therefore, what we do is a sort of clustering with the aim of stratifying our cohort of patients. Therefore, what we apply usually are clustering methods and mostly combine with dimensionality reduction methods that allows to provide a better description of our features and to assign to the patients new labels that are able to group the patients that can develop a similar prognosis. On the other side, another type of approaches that we are using are the supervised ones. So in the supervised, we provide the features and the outcomes together with the labels. Here, the aim is to try to find out the rules that best identifies those labels and therefore to classify well the patients. In order to address this task that we call prediction, we have to split our data from our cohort of patients in two sets. One of training, where we use the features together with the outcome in order to train the model and find out the best rules, and the other set that is called a test set, where we have the information of the outcome of our patient, but we apply the model that is already trained on the new data using only the features. The model will automatically provide the prediction that will be compared with the known outcomes, and in this way we are able to assess the performance of our model with the aim of making generalizable model, in order that if another cohort is coming from another center, clinical center, with the same prediction task and data, we expect that that model will perform the same performance with the same accuracy. We can then complicate our outcomes. Therefore, we can pass from an outcome that is characterized by a set of, for example, binary classification and to do cross-sectional, we can move towards longitudinal analysis, where we associate to the outcome also the time. In this way, we are able to predict at which time a specific event will occur. And this is allowed through survival analysis. That is a crucial tool that aims to predict the time to an event of clinical interest at an individual patient level. In this setup, we will have then the information about the start of our study, for example, the date of a diagnosis of a specific disease, and then we will fix an end of our study, and we will observe how many patients will develop or not a specific outcome. In this way, we can describe our cohort by associating what is called the survival probability, therefore the probability at each time of the follow-up, where we can predict how many patients will develop a specific outcome. The basic statistical approach is the Cox regression model that allows a linear combination of the features. Therefore, what we do is summing all the features that we want to include to our model, and each feature is modulated by a weight that is predicted by the model in order to have a combination that achieve the best performance. In the last year, there was a further development in machine learning methods. Therefore, from the plethora of methods available from machine learning, neural networks and now deep learning methods are showing better performance in terms of accuracy of the results. And another main advantage of these methods is to achieve a better representation of our feature by allowing also nonlinear interaction among the features. So by combining them, it is possible to test new algorithms starting from around 2018, these new algorithms are available for making this type of prediction of the prognosis. So a first application, we already tested this algorithm to the use case of myelodysplastic syndrome, where we have a cohort of more than 2,000 patients, and we consider three types of events: the overall, leukemia-free, and event-free survival. In addition, we are moving towards a single machine learning application using only clinical data towards a multimodal approach where we try to combine multiple different information from the patients. In this case, for MDS, we try to integrate clinical, demographic, cytogenetics, and genetics data. Of course, this task is more challenging for us because we have to deal with high dimensional and quite heterogeneous data that can contain several missing information. So here we try to test this data and compare them to the classical approaches, also using different integration strategies. So we start by integrating demographic and clinical variables, then adding the genetic information, and then we try to substitute the genetic information with a more compact representation through scores or clustering approaches that are able to compress the data. Here is the preliminary, these are the preliminary results that we obtained by our assessment. In the y-axis, you can see the concordance index. The higher it is, the better the model performs. And we can notice three characteristics of these results. The first take-home message is that we need the genomic data, since using only demographic and clinical data reduce the performance of the models, of all the models. If we focus on the linear approaches, we can see that using the data as they are not enough. So we need to pre-process the data by compress the genetic information in order to increase the performance. On the other side, for the nonlinear approaches, the machine learning-based approaches, we can see that this step that is it's a high-level pre-processing that requires time in order to find out the best compression is not necessarily required, since the performance are pretty the same. However, we are now wondering whether if we combine together, since these are two steps that are separated between each other, if we try to combine unsupervised with supervised approaches, we are able to further improve the performance, starting from the MDS data that we know that are characterized by heterogeneous group of hematopoietic stem cell disorders, and it's very tough to find out a good representation of the data. So what we are testing now is a new framework based on neural networks that tries to predict the patient's prognosis and at the same time identify genetic-based cluster of disease. What it does is try to perform a first neural network on the genetic data, where the models learn a sort of latent representation of the genetic data, and then combine this data with the clinical features in order to feed another neural network-based approach for the survival analysis. And the results that we obtain are quite encouraging because we can see clusters that are well characterized since they are able to identify specific groups of mutations in the patients, and also the groups of patients identified shows different profiles in terms of survival probabilities. Another challenge that on which are working on is making all these models explainable, because usually in clinics machine learning is not well viewed, because compared to the statistical approaches it's tough to find a good interpretability of the features. But also for this point, there are new approaches that enable to clearly show which features are impacting most on the final model. And also we are able, for each patient separately, we can also list the features that best represent the prognosis of that patient. So this is a powerful tool that we are trying to integrate in our frameworks. The next step of our work is to extend this analysis also to the other use cases. So for sickle cell disease, we will soon have the genetic information, metabolomic information, and clinical data. And in addition, we also have the radiomic features from 1,000 patients, while for the multiple myeloma, we will have radiomics, copy number variance information, and clinical features. Of course, all these frameworks will be then adapted to federated learning approaches that allows the distribution of the models across multiple centers, and that now Patricia will talk about. I would like lastly to thank all the collaborators of my lab, so Piero Fariselli and Cesare Rollo. Thank you for your attention.
Thank you very much, Tiziana. So I can ask now Patricia to take the floor.
Okay, so first of all, hello everyone, and thank you for attending our webinars today. As Mariangela already said, I'm Patricia Alonso. I'm professor and researcher at the Universidad Politécnica de Madrid in Spain, and I'm currently finishing my PhD in machine learning techniques applied to the medical field. I'm actually an engineer, so my background is mainly technical, but for a few years we have been observing that there is like a really big opportunity to offer our technical knowledge in this field. Sorry for my voice, I'm a little bit ill. In the GenoMed4All project in the UPM, in our work package, we are in charge of implementing several machine learning methods in federated environments. So basically, we are trying to solve specific tasks, as Tiziana already said, for example, survival analysis in 3 different diseases, 3 different rare diseases, but in a federated environment. So this is what why I'm here today. This is what I'm going to talk about today. In addition to trying to explain like the basic concepts of federated learning, I will try to put you in context by showing some preliminary results of what we have been achieving in the project for those rare diseases. So I will try to be as clear as possible, and I will try to avoid any technicalities. But of course, if there is something that you don't understand, I will be more than happy to try to answer your questions during the question time slot. Okay, so for those of you who are not familiar with the concept, I would like to pose an idea or a question that may have crossed your mind at some point. So have you ever wished like that medical care was a little bit more personalized, and therefore more effective, or even simpler? Have you ever wanted medical research to advance faster? I think that all of us gathered here today, patients, professionals, health enthusiasts like myself, we all agree. I mean, like 2 or 3 years ago, I think that idea passed through our minds during COVID time. So I think we all might agree on that. The faster we can develop and validate treatments, new treatments and or new interventions or new medicines, the more lives we can potentially save. So we all know that medicine is in a constantly evolving field driven by technological and scientific advances that seek to provide more precise and more personalized medical care. In this context, federated learning presents itself as a tool, an essential tool, not only to improve efficiency in medical care, but also to address different challenges, for example, in handling sensitive data. I have gathered those challenges that I consider most important in the next slide, and I will try to clarify them. So the first one, I have already mentioned it, and I think it's the first one that comes to our mind when thinking about federated learning is data privacy. Protecting the privacy of the patient is a must, is a priority in the medical field. Traditionally, sharing medical data for research was a little bit risky process because it could expose confidential information about the patient or about the hospital or about the research center. Federated learning allows data to remain on local devices, on local places, on a single hospital, the hospital where the data was generated, without the need to be transferred to a central server or to another hospital. This way, security and privacy risks are mitigated. Completely related to this challenge, we have the next one, which is global collaboration. In an increasingly interconnected world as we live in, global collaboration has become essential to advance in any field of research, but of course, mainly in medical research. Federated learning allows institutions around the world to work collaboratively in data analysis without the need to share information. This speeds up a lot the research process and therefore leads to faster medical discoveries, for example. And thanks to these two concepts, these two challenges, federated learning is able to personalize treatments. I don't think this is like a direct challenge for federated learning, but it is a direct consequence of federated learning. Each patient is unique with a combination of genetic, medical, environmental, lifestyle factors influencing their health. Therefore, I think we all know about this. There is no such thing as all the patients responding in the same way to a generic treatment. How does federated learning address this? Well, thanks to the collaboration that I already defined of different institutions around the world, we can have a much larger study of cases of patients with the same disease, for example, but with very various clinical medical histories. In this way, a professional, a clinician, can achieve a more personalized treatment. The next challenge would be accelerating the research. I think we all know, and I've been getting used to this for the past years. Medical research is often blocked by the lack of access to data. Maybe because of privacy or simply because there are not enough samples to create a big data set. Federated learning overcomes this challenge by allowing access to globally distributed information, not globally distributed data, but information. I'll talk about this later. and driving research and treatment development faster than ever. And finally, the last challenge that it's always described in the implementation, development, or research of any technology is the cost. By removing the need to transfer data to a central server, federated learning decreases costs associated to, for example, storing or managing medical data. This makes medical research more accessible to all of us. And well, I think that these challenges are remarkable to try to make you see the motivation in using this type of learning in the medical environment. But despite giving you the reasons to believe in federated learning, I have not yet explained what federated learning is. So what is the process that, for example, an AI model follows in a federated environment? In this next slide, I have written a possible definition of federated learning. Federated learning is a decentralized machine learning approach that enables models on distributed data without the need for data sharing, with bringing privacy and scalability benefits to the field of AI. There are lots of federated learning definitions. I took this one because I think it's a clear one, but let's take it one step at a time. So the first part, federated learning is a decentralized machine learning approach. What does this mean? Well, it refers to to an approach where instead of having all the data stored and processed in a single location, in this decentralized approach, the data is kept in the hospitals or centers where it was generated, as I said before. This allows the machine learning model, the AI model, to be trained at each location without moving the data. But how do you achieve information sharing without moving the data? That's the key question of federated learning. I haven't been thinking of a way of explaining the process without going into much depth. And I thought that the following example is easy to understand because I think it will sound familiar to all of us. Imagine that there is a group of people who want to work together on a project, our case, but each of them has valuable information that they don't want to share publicly. I would think that the process would have like the following steps. First, people meet and agree to work together on the project without having to share all the details of their information. That's the basis. Then each person would do their own analysis with their own data separately from the other ones. As the project progresses, every X time, every, I don't know, 2 weeks, for example, people will meet to share what they have learned, but not what to share their data. They share updates and conclusions of what they are learning, okay, not the data. Then, based on the shared updates from every person working in the group, the group collaboratively works on making a global solution where each update helps making this solution more accurate. Okay, and then finally, after lots of meetings working the same way, at the end of the project, useful results will be obtained without the need of having to expose their own personal data. This is exactly what would happen in a real situation where several hospitals work to improve their models, but without sharing sensitive information about the patient. Each one trains its tool, let's call it tool or model, with its own data, and every X amount of time, information about how the tool is performing is shared, but not about the data, just information about how the model is performing. With this shared information, what would be a global tool, a global model is generated, and it is improved thanks to the information from each update, local update. And then learning can continue from there. This is exactly what the slide illustrates, this figure taken from NVIDIA. But I think that's enough explanation. I don't want to go into more technicalities of, for example, AI algorithms or how the communication between the different locations works. But I hope that like the idea is clear for you. Data is not shared. Information about the tool, about how the tool is working, is shared. Okay. So before going into examples of what we have been achieving in the project so far, I would like to comment briefly that although this learning technique sounds very promising, it is not all plain sailing. Federated learning presents challenges that need to be properly addressed, especially with regard to the following factors that I have written down in the slides: privacy and security, communication, bandwidth, model coordination, data heterogeneity, latency, etc. How do we ensure that our data is secure while training these models? Or how can we make communication between the different devices safe? Or how do we ensure that the devices are synchronized? And finally, a more simple one, how can we evaluate a model without having the data? These are questions that that need to be answered. So to address these challenges, a really careful approach to the design and implementation of federated learning systems is really, really essential. I mean, what I want, the idea that I want you to get is that it's not all nice and simple. There is a lot of hard work behind the design of federated systems, in which lots of factors have to be taken into account. Okay. So finally, I wanted to show you the progress of how the use of federated learning for several tasks using AI models is benefiting our experiments. So far, we have only obtained data. Well, we have only obtained results for two diseases, for the MDS one and for the multiple myeloma, the MM1. So in this slide, I'm showing you results for the first one, for the MDS. Just a brief explanation. I have used we have used a AI, a deep learning model, just as Tiziana showed you, the BAE framework. It's a similar one. We have used that model training with the MDS data, which again, it's a really, really high dimensional data set, and it has really heterogeneous data. So it's a complicated data set to train a model. We have performed survival time analysis for MDS, and we have validated our results in terms of C-index. As Tiziana said, the higher the C-index value, the better. And in these experiments, we wanted to simulate a real-life situation in which 3 different hospitals train each one a local model with their own data. You can see in the slide, instead of hospitals, it says nodes, but the same. So I'm showing you results here for 3 different experiments. Scenario 1 is a simulation where every hospital has the same quantity and quality of data. I think it was like 2,000 samples each one. You can see that the curves show a really similar performance for each hospital, which makes sense since the data it's really similar in terms of quantity and quality. You can see that every 20 iterations or every 20 epochs, there is a peak in the representations. This peak represents the federated learning sharing step. Okay, once the local information from the learning process, sorry, once the global information is return to each local hospital, these hospitals can start learning from that again. So that's like the whole process. In this scenario, you can see that federated learning does not help at all, but because the hospitals have the same quantity and quality of data, and because of the data set itself. In the next two graphs, you can see that there is a hospital that begins showing a worse performance compared to the other two. This makes sense because this hospital 3, node 3, in scenario 4, is worse than the other ones in terms of quantity and quality of data. You can see that there are two graphs. One is scenario 4 and 100. That means that the hospital 3 has 100 samples. And the other one is like a really, really, how could I say this? Like the worst performance we could obtain, because the hospital 3 has only 10 samples, which is absolutely useless for a deep learning model. So we can confirm watching this the different representations and the different curves that federated learning process helps this node, this hospital, to reach the other ones after some iterations. Hospital, well, scenario 4, 10 samples lasts a little bit more than the other one, but because it has less information. So every time model information is being shared, it achieves a little bit better performance. Okay, so we can confirm here that federated learning works somehow, helping the worst hospital, the worst location, the worst performance to achieve better results. So the next slide. In this slide, I'm showing you numerical results, not graphical, for the other use case. I thought that maybe numerical results were more easy to explain, of course. And in this case, we have, well, for this dataset, we have performed a classification task, not survival analysis task, in terms of early relapse, whether the patient achieved or not the early relapse. In this case, we have used a different model. It's just a logistic regression model used to classify. And the dataset itself is a dataset with really few samples. And you can see that it is, we have divided the results in terms of therapy, because the patients are divided in terms of therapy. Okay, so in this case, we have used a metric called F1 score, and the higher this score is, the better. So we can confirm that training in an isolated way, which is a way where there is no federated learning, there is no sharing information. This way, we obtain worse results than sharing information. For example, if we focus on a scenario 3, where there are two hospitals that have similar quantity of data, and the third one, again, has only 10 samples, the results obtained in an isolated way are lower for the third one. But once information is shared, the results improve a lot. So this is all I wanted to show you today. I hope that at least you go back home with like the idea of what federated learning environments are. And of course, with the idea that this kind of learning improves models' performance in some situations, for example, where data, where there is a scarcity in quantity of samples, or there is poor quality of the data. And I think that this is something that can be extended to the real world. It really happens in real world. So these preliminary results are really, really interesting. I also wanted to highlight before ending that although I have focused on in the medical field due to the people we are gathered here and the nature of the project, this kind of learning can be applied to any other field. So it's a really, really interesting learning process. And I think that's all from my side. So thank you very much for listening. I hope that it was not that boring, and I hope that I have shown you in some way what a federated implementation is capable of helping in the medical field. So thank you very much.
Thank you so much, Patricia, and it was very comprehensive and clear. So now I will pass the floor to the last speaker, Gastone.
Okay, good morning. Okay, my name is Gastone Castellani. I'm in charge of work package 6, that is the artificial intelligence. And yeah, in the European project GenoMed4All, I will give you introduction, panorama about the data integration and some analysis. In GenoMed4All, we have 3 use cases. That is multiple myeloma, myelodysplastic syndrome, and sickle cell disease. And the type of data we are collecting in this project are dependent from the use case. For example, in the case of multiple myeloma, we will have some genomic measurements, especially copy number variation, and medical imaging measurements like CT, computerized tomography, and PET, that is a positron emission tomography, because this technique has been proved to be very useful in the diagnosis of multiple myeloma and also in the stratification of patients. In the case of myelodysplastic syndrome, we have basically genomic and clinical data. Of course, also in the multiple myeloma use case, we have clinical data. In myelodysplastic syndrome, we have basically target sequencing and clinical data, clinical measurement. In the case of sickle cell, we have medical imaging data, basically magnetic resonance and metabolomic and another type of genomic data that is I don't remember the name, but is a kind of not copy number variation, but is a kind of array for some mutation in sickle cell. So I like to start with this slide because this is a famous motto from this guy that was a statistician or a data scientist, might be the first data scientist in the 50s. And we are very dependent from data. Without data, it's not possible to do anything. Of course, we will need also to aggregate, to integrate this data, but the first ingredient is to have data and the data with a good quality. I have to mention also Harmony, that is a project, another European project that is studying oncohematological diseases, and GenoMed4All actually is collaborating with Harmony. Harmony is, I think, is the biggest project in the world about oncohematological diseases. This is a first idea of data integration. So we have data from different layer of complexity, starting from the molecular layer, and so metabolomic, genomic, etc. And across this layer of complexity, we can reach also the medical imaging. Actually, we have also cytological and histopathological images, and we are working in the integration of this layer. There are several methods for integrating this data. Now, I don't want to describe in detail this method, but in this slide, you can see what is called a multiplex. A multiplex is a generalization of complex network. And so each layer can be analyzed with technique, more with bi-complex network, and we can have also intra-layer connection. So basically connection between different layer of complexity. There are also other methods for data integration. I will discuss just multiple myeloma, in which we are trying to integrate the radiomic approach with the genomic approach. As Patricia was saying, GenoMed4All, one of the pillars of GenoMed4All is the federated learning. And I don't want to spend time in describing federated learning. I can just say that federated learning is a way to overcome the problem of data sharing. So we hope that federated learning can help to have a kind of open data, open space. So basically, as Patricia was saying, we are moving the algorithm, not the data. Okay, this is a pipeline that can be used also for data integration. This is one of the simplest data integration because in the case of myelodysplastic syndrome, we can integrate between genomic variable and cytogenetic variable. What are these two variables? Genomic variables list of mutation in well-known gene. So this is called target sequencing. So expert in oncohematology selected a number of genes that can be relevant for the diagnosis and the stratification of patients. This is true for MDS, for myelodysplastic syndrome, but this is also true for acute myeloid leukemia. By the way, myelodysplastic syndrome in the worst scenario can generate acute myeloid leukemia. So it's very important also to be able to predict the transition from myelodysplastic syndrome to leukemia. So genomic variable, and the other variable that we can integrate are cytogenetic variable. Cytogenetic variables are, let's say, mutation on a larger scale. So deletion, insertion, duplication, etc. A lot of these mutations are important in the diagnosis of myelodysplastic syndrome, but also in acute myeloid leukemia and also other diseases. And of course, we have also clinical variables. A similar approach can be used also for multiple myeloma. And in the case of multiple myeloma, we have to use copy number variation. So basically, some region in the genome can be amplified, or we can have amplification or a deletion of some region. So basically, this pipeline that can be also implemented in a federated way is clustering. So clustering means to stratify patient, to identify this cluster. And after this stratification, we assign patient to each cluster of mutation and cytogenetic alteration. After this step, we can compute, for example, some clinical outcome. In this slide, I'm illustrating a typical clinical outcome that can be overall survival or progression-free survival, etc. And I think that Tiziana was showing some very advanced technique for performing this analysis. So clustering patients and computing of some clinical outcome. We can also, by using Bayesian network, and Bayesian network can be also implemented in a federated way, we can assess the causality between mutation. So if one mutation is causing the insurgence of another mutation, etc. And finally, also we can assess about the temporal scale of this mutation. This is called Bradley-Terry test. So this is a very generic pipeline for genomic variable. In the case of radiomics, the idea is very similar, is in some sense similar. So if we have medical images, so PET, CT, TAC, etc., we can, after segmentation, after the identification of a region of interest, we can segment this region, and from this region we can extract feature. This feature can be morphological and can be a texture feature. By using ad hoc software, we can extract, let's say, 1,000 of this feature. We can also extract this feature by using a convolutional neural network, a multi-layer network. And after this feature extraction, we need to perform feature extraction and dimensionality reduction. So basically, we have to identify the most important feature for predicting some clinical outcome. The clinical outcome can be, as in this case, response to therapy, overall survival, progression-free survival. This is depending from the desiderata of the clinicians. But the problem from a computational point of view is very similar to the problem we described in the case of genomic data. So we have tabular data. The rows are the patients and the column are the feature. And we want to use this feature after feature selection and dimensionality reduction. We want to predict some clinical outcome. Yeah, this is a pipeline. I don't want to describe. I don't want to describe all this pipeline. This can be used for 2 use cases: myelodysplastic syndrome and multiple myeloma. Let's say for the part related to genomic data in multiple myeloma. So let me just describe the most important step. One of the most important steps, in my opinion, is the dimensionality reduction. Because if you want to use also a simple model, a logistical regression or a perceptron or a simple artificial intelligence model, you have to reduce the complexity of the data. And this complexity can be reduced by using dimensionality reduction. Basically, dimensionality reduction is a way to identify the most important feature capable to predict the clinical outcome. And another important step is the clustering. For the clustering, there are several methods. Some methods are easy to be federated. Other methods are not so easy to be federated. And so we are still working on this trade-off because our gold standard is a method that is not easy to implement in a federated way, but there are other methods that can be implemented in a federated way, and so we are trying to compare their results. Okay, I think yes, I forgot, but it's written here. Another very important problem for data analytics, but also for data integration, is the missingness and the quality of data. Usually, in every clinical data set, we have missing data for a lot of reasons, because a patient don't finish the study, or so it's very important also to correct the data for the missingness. And there are procedures that are called imputation procedure that can impute the missing data. But this is a very important problem that is related to the quality of data, and also EMA is very interested in approaches for impute data in a very efficient way. This is another pipeline for radiomic. Actually, we implemented this pipeline in GenoMed4All. Basically, also this pipeline is concerning about pre-processing of images. In the case of imaging data, we have to perform a heavy pre-processing. So denoising, registration, etc., segmentation, etc. And after this, a first feature extraction by software and ad hoc method. And after this feature extraction, dimensionality reduction, clustering, and prediction. So this is one example. In the case of multiple myeloma, this is one example on how we integrate a different measurement. So in the case of multiple myeloma, PET is a very important technique, because PET is capable to identify the region with a high metabolic activity. But in order to localize this region, we have to merge and to align PET images with CT images, because PET is just a functional procedure and is not giving you information about the anatomy of the patient. So we have to overlap PET and CT. This is one example of segmentation of CT scan. And this has been performed in collaboration with UPM, with the group of Federico Alvarez. They are using a particular software that is called Moose, and we are comparing results with another method developed by our group. And this is the overlapping between PET and CT. So you can see that there are some regions that are very active from a metabolic point of view, the brain, the liver, etc. But we are interested in lesion near to the spinal cord, because these lesions has been classified by a medical doctor as lesions that are very important for predicting the outcome. And so we performed a method to identify automatically these kind of regions. and this is a preliminary result. PM means perimedullary lesion. So if there is an involvement of this lesion, the survival is lower. And so this is a first result. This is just a Kaplan-Meier curve. So we hope in the future to use also other more refined method. But this is just an indication that the involvement of this lesion or the identification of this lesion is very important. Another example is the identification of silent infarct region in sickle cell disease patients. So in this case, we have MRI images, and you see these white matter hyperintense region are these small regions that are also very difficult to identify by eyes. So in collaboration with the University of Padova, we used a software that has been used in the case of multiple sclerosis. And this software, after the supervision of an expert radiologist, neuroradiologist, was able to identify this region. And you see that we have also to post-process the images because the ventricular area are identified as possible white matter hyperintense region. So we have to eliminate this false positive. But now the results are enough good. So after this identification, feature extraction, and we repeat the pipeline I was showing. So just to finish, this is, let's say, the idea, the long-term vision. So by using this multidimensional and multi-omic data, we will be able to extract feature in a federated way, to integrate this feature, and to build a surrogate model that can be a kind of a digital twin that can be useful for diagnosis, prognosis, hopefully therapy, etc. And thank you, and this is all.
Thank you very much, Gastone, for this presentation. So now we have, as announced, more or less 20 minutes for the discussion. So I see there are already questions in the chat, but I will ask first my colleague from Australia to check in the Slido if...
There we go. Yeah.
Thank you. So the first one, do you envision patients will also have access to AI healthcare tools in the future? For example, for self-monitoring their disease at home? Thank you. Who wants to pick this big question? Who is brave enough?
No, I can say something, but this is not related to GenoMed4All.
Please,
So,
I mean,
yeah,
you are
no,
experts, so we accept every answer.
Just one example, classical self-monitoring can be obtained by a technique that is called photoplethysmography. Photoplethysmography is a technique that is capable to give a surrogate of electrocardiogram, but also can inform you about the state, the elastic state of arteries. So by using artificial intelligence, but also statistical learning, you can assess the so-called vascular age. The vascular age is different from the chronological age because in some individuals, as a function of diet and lifestyle, etc., the aging process in the vascular system can be different from the chronological age. And so a quantification of vascular age can be performed at home automatically, etc. Otherwise, some artificial intelligence software can also collect the self-reported outcome. And so patients can inform the software and medical doctors about their state, etc. So all the method based on sensor, on wearable, can be used for this at home.
Thank you. So if Patricia and Tiziana do not want to add anything on this question, I will go to the second one, but please stop me if you want to add anything. So heterogeneity was mentioned as a challenge in federating learning. In rare diseases, will data fragmentation also have a negative effect on results? Thanks.
Okay, so I think that data fragmentation is going to have negative effects in not in federated learning itself, but in the use of any AI model, any machine learning model. The data has to be really good pre-processed so that the AI model works. Of course, if the quality of the data is not that good, the AI model won't work the best, and the federated learning will be useless. So, as Gastone said, any model, any machine learning model depends on data, on how data is stored, how it is pre-processed, where it is pre-processed. So I think it will also have negative effects. It has to be the previous step to the federated learning part has to be the best, really well organized and really clear, so that the federated learning process makes sense. So I mean, I think it will have a negative effect on the results. I don't know if maybe Tiziana or Gastone want to add something, because they might know more about data fragmentation.
No, but you are the expert of federated learning, Patricia. So I leave the the floor to you.
Thank you.
Okay, so we'll go to the next question. Regarding federated learning, should the hospital provide which variables are in their file in order for the developer to simulate similar data?
What does simulate similar data mean? I mean, I think that well, the hospital can, if there are legal or privacy concerns, the hospital won't share at all the content of the data itself. So there is a problem there, because if some hospitals have some, for example, some variables refer to some experiments, but the other hospital has other variables refer to other experiments, the model itself will, I think it will crash when trying to aggregate the updates. So this is like I don't know how to explain this. I don't know how to explain this. I think that the hospital, I don't know if Gastone was going to say something. I don't know.
No, yes. Sorry, Patricia.
Okay. I mean, the hospital is not going to share the information about the data set, and that concerns the variables itself, themselves, of course. But there has to be like general model where the local updates are aggregated, that can be scalable to many variables. I don't know if this makes sense.
No, the only that I can add about the simulate similar data is synthetic data generation. So it is possible also by using the real data as a template to generate data that are called synthetic data with the same statistical properties of the original data. And these can be used for training a neural network and or artificial intelligence models.
The results that I showed in the presentation, they were obtained with simulated data. Since we have really few samples for each data set, really few regarding the deep learning model, of course. Since we have really few data, we simulated new data, but that is done in a local device that is not federated, that is not shared. Okay, that's everything I can say.
Thank you. So I move to the next one. About the shift from a centralized to a federated implementation, does quality matter more than quantity? For instance, fewer HQ samples are preferable than high quality samples are preferable than?
It depends more on the type of model you are using, not on the federated implementation, I think. The kind of model that you're using can be more sensible to the quantity or to the quality of the data. So it depends more on the model. There are models that can work with few samples, but if the quality of the data is really poor, for example, there are lots of missing data from X variables, the model can work really bad. It depends on the model, not on the federated implementation. Of course, if you have few samples and the quality is really poor, then it's really difficult for a general model to work. But it does not depend on the federated implementation.
Thank you. Does Gastone or Tiziana want to add anything? Or I will move to the other question. So the the benefit of the FL approach are clear in terms of performance only. How does the FL model compare with the centralized one that will use the whole dataset?
The aim of the FL implementation is to achieve the more or less the same results as a centralized one with the whole data set. So that's the comparison. The aim of the FL system is to achieve what a centralized system with the best quality and higher quantity of data could manage. So that's what we are trying. The thing is that when trying to explain our results, we try to compare them to something we call the upper bound, which is a centralized model with the whole data set. So that's our aim. Of course, it's depending on the model and on the data in each different hospital, for example, it's really difficult to achieve that upper bound, but that's what we are trying to do.
Thank you. So I will go to the next question for Tiziana. What is your approach to select the most suitable confounding factors for the survival model, apart from age, sex? Thank you.
Yeah, that is a good point. So there are different types of approaches that we can consider. So there are some models like the penalized regression models that allows to estimate also the weights in a way that we directly perform the feature selection, because some weights that are estimated from the models can be 0. So putting into 0 the weight of that specific feature, we can automatically perform the feature selection. Otherwise, with other methods that in any case estimate tries to give also a minimal score to the feature, we can complicate more the training phase by doing further cross validations that allows to find the best set of features that performs the best for the training data. And of course, we hope that in the test data, they can perform as well as best. One point, we need to be very careful in this type of operation because since we need to increase the steps in the cross validation, and if we have not so many data available, there is the risk to have a sort of overfitting of the model. What I mean? It means that the model is it fits too well on the data that we are considering both for training and for test. And if in the future we have to use that model again in another cohort, we do not achieve the same results. That means that the model is too fit to that specific type of data. Yes, I think I said all the major points related to the feature selection, but if there are some questions, let me know.
Thank you very much. So next question. Yes, I see we have more or less 5 minutes. So quality of data has been a concern for some data of the artificial intelligence funded project. What advice can you give data providers for future participation?
I think I can answer this. The first to the data provider, the first hint is about to fulfill the request from the people that are trying to standardize this data. Because, so for example, be sure that the outcome, the clinical outcome, has the minimum, or as is possible, the minimum missingness rate. And the other hint is to check the missingness mechanism, if it's random or not at random. And yeah, and of course, try to provide data with the minimum percentage of missing data. Also check about the quality, about the measurements, how the measurements are expressed, etc. But in general, in all the European projects, there are some standards that have to fulfill. So the golden rule is try to fulfill the standard that the project is asking.
I would like to add one thing to what Gaston has said. Of course, if there is a standard, just follow that. But one thing that I have encountered a lot is the dimensionality of the data. There are sometimes if you have few samples, few patients, and you have lots of let's say if you have a CSV, you have lots of columns of variables, and really few samples, that won't work in an AI model, in a deep learning model. You have to reduce as much as you can the dimensionality. Maybe try and leave the main variables that are most important for what task we are going to perform. So the dimensionality is a really important factor.
Thank you. Thank you very much. So I will pick the very last question. What is Bayesian network? I don't know if I pronounce it. It's not a 1 minute question answer, I guess, from your expression.
So very quickly, a Bayesian network is a graphical probabilistic model in which the conditional probabilities are setting the links between nodes. And so by using this conditional probability, you can assess about causal relationship between object, let's say mutation or other object.
Thank you. Thank you very much. I'm sorry we cannot tackle all the questions, but it's a good sign because it means that it was really a necessary and crucial topic to be tackled by a webinar. What can I say? Thank you very much to the 3 experts with us, sharing all their expertise and also the time with us. That's very much appreciated. And thanks for the audience for this incredible interactive debate, and also to my colleagues of Australia and GenoMed4All for coordinating all of that. So this was the last session of a program for public at large. Thanks, really thank you a lot. And videos will be soon available on YouTube of the 4 cycle of webinars. So have a nice evening. Thank you very much.
Thank you.
Bye
Bye.
bye.
Thank you very
Bye-bye.
much.
Bye.